Okay, thank you for the invitation, and I'm sorry I couldn't be there in person. Okay, today I will talk about some new approaches towards constructing test vectors in uh, Euler systems. And this is all joint work with Cai Li and Fan Yu. To start with, uh, okay, let me, the entire talk will be focused on two different settings. So I'm going to explain both of them at the same time. So our setup is, let's see. Okay, we have two algebraic groups G, and we assume they have Schimmer varieties, Schimmer H and Schimmer G. If we have such an embedding of Schimmer varieties, we can push forward the class of the smaller Schimmer variety to the bigger one. So this is the top degree cohomology class of the smaller Schimmer variety. And we can push it forward to get a class. Oh, well, we get a cycle class in the bigger Schimmer variety. And we can also take its periodic realization, which lies in something called the continuous cohomology. It's some version of motivic cohomology for cycles. Well, this is a case of motivic cohomology. In this case, it's just concretely cycles. And was and this squiggly arrow is doing a lot of technical work, but modulo a bunch of technical issues. Starting from such an elementary completed cohomology, we can get a class in Galois cohomology, where here E is the reflex field. And P is the Galois representation. And the thing I want to draw attention to is this is integral coefficient. This is ZP and not QP. Okay, so this is just a purely abstract setup. Now I'm going to give you 3 examples. I'm going to take E over F to be any CM extension, but concretely K over Q, K imaginary quadratic is good enough. So the basic example is Higner points. Here G is GL2 F, so its Schimmer variety G is just modular curve. Okay, in this case, I really probably should put Q here and imaginary quadratic. Yeah. Okay, I will make that correction. And here H is the restriction of H is basically a torus, a non-split torus. So its Schimmer variety is just a bunch of points. And this embedding of Schimmer variety H into Schimmer variety of G has image CM points on the modular curve. And those were classically used by Higner to construct points on the elliptic curve, modular curves and the elliptic curves. Now, this example can be generalized in 2 different directions. Both 2 and 3 are generalizations of the first example. In example 2, we take G to be a unitary group in 2 n variables, and H to be 2 unitary groups in n variables each. And this just represents signature. So if n equals to 1, G is U11, which is up to isogeny GL2. Yeah. And H is up to isogeny a torus. So that's the Friedberg-Jacquet case. And another generalization is the Gangros-Prasad conjecture, which was we had a mini course on last week. In this case, H is just a single unitary group of n variables. G is a product of 2 unitary groups. And if n is equal to 1, yes. This G is again basically GL2 up to some abelian factors that I'm not going to worry about. So both of these specializes generalizes the Higner point case. Okay. The reason we chose these groups is because they have a common feature. When I switch slides, you don't see the notes. Okay, doesn't matter. So the common feature is the resulting cycles that you get if you compute the dimensions of all the Shiba varieties. It's in the middle dimension, arithmetic middle dimension to be precise. In this case, we have conjectures that predict the height of the cycles should be related to derivatives of L functions. And in the Higner point, this is a theorem of Gross-Zagier, and later generalized to more general settings by Yuan Zhang, Yuan Shouwu Zhang, and Wei Zhang. So those are essentially in the Higner point case. And later, Wei Zhang formulated the arithmetic. So the arithmetic GGP conjecture was already formulated in GGP, but Wei Zhang gave a more precise formulation later. This is still wide open as a conjecture, but it predicts some relations between the height of the GGP special cycle and the derivative of certain reconcilable L functions. Okay, so the upshot is in these specific cases where the cycles happen to land in the middle dimension, they should have arithmetic significance. So one goal of basically this talk is we want to extend this ZP. Remember, this ZP was an element in Galois cohomology. And we want to extend it to an Euler system. I'm going to give a definition of an Euler system later. So we want to extend it to an Euler system. And in the cycles case, we want to extend it to something in the sense of Jeshev-Nicovar-Skinner, which is slightly different from the Euler system stuff that Skinner and Marco was talking about last week. But if we can extend it to an Euler system, then Jeshev-Nicovar-Skinner tells us essentially if the base class, this ZP, so this special cycle, is non-zero in Galois cohomology, then the Bloch-Kato Selmer group has rank 1. So rank 1 case roughly says ZP non-zero in Galois cohomology implies, let's say, rank of H1 Bloch-Kato F ET is equal to 1. I'm not being very precise about exactly which automorphic forms I'm taking. This is just the general shape of the result we are expected to prove. And in this case, let me give you the key point of an Euler system. So the key step in this extension is for all but finitely many F places L. So L is a place of F, and I'm assuming it splits in E, but this is part of the axiomatization of Jeshev-Nicovar-Skinner, and different axiomatizations of Euler system have different conditions on the place. But in any case, we want to construct a class that doesn't notice that we are not taking cohomology over E, we are taking cohomology over EL. This E square bracket L means the ring class field of conductor L. So this is an anti-cyclotomic extension of E, which is ramified exactly at L. Notice that before, for the base class, we are not doing any base change here. This is just the absolute Galois cohomology over the base field. So now because we're doing this base change, the usual Abu-Jacobi stuff will give you a Galois cohomology class in H1ELT. Okay, and it needs to satisfy a norm relation, which is the trace, when you take the trace down from this ring class field down to E, you get the base class up to a specific Hecke operator. this is supposed to be the local L factor. E inverse. I mean, to be precise, in the Euler system formulation, this is a characteristic polynomial of Frobenius. But in the cases we consider, this characteristic polynomial will be a local L factor. So to extend this base class Satake to an Euler system comes down to constructing a large collection of classes. Basically one for each place L.
Can you hear me?
Yes.
Hi, Kazim here.
Hi. Was there a question?
Able to hear the question, Shilin? Maybe is it on?
I did not hear anything.
Okay, hang on one second. Just hang on 1 second. Here, try this.
I'm sorry. Now you can probably hear me. I'm just saying like this seems different from the Heegner points. Then they satisfy like a three term relation, no?
Yeah. So modulo L minus 1, they are the same.
Modulo what?
Modulo L minus 1. Where a norm of L minus 1. Modulo the size of the residue field.
I see. So I mean this relation happens modulo L minus 1 or like the whatever it was.
I see. To actually use an Euler system, you only need this relation modulo L minus 1.
Sure. Okay, I see. Okay, so it's not a characteristic zero relation. I get it. Thank you.
But we can prove this in characteristic zero.
But again, it's like different from what the Heegner point satisfies in characteristic zero. That's what I'm saying.
Yes.
Okay. All right. Thanks.
Okay. To get this collection of classes, I will mention 2 ways. So the first way is to modify the classes by using Heike translation. This result is known for quite a while, but one part of our work is to get this down at the integral level. So what this specifies is integral functions taking integral values maps to cohomology with integral coefficients. This is a key point of our work. And for this, we need to take functions valued in this variety G mod H, which happens to be a spherical variety. But so I don't want to spend time on this, but this is, if you are familiar with Euler system stuff, this is the usual modification. This is the usual like Heike translation, just packaged together in a nice way that preserves integrality. But the upshot for us is we have a systematic way of producing a large collection of Galois cohomology class. And just by choosing smooth, compactly supported function on some variety X. And another input that has been used in this Euler system literature is how do we get this field extension? How do we get this EL? Well, the way we get it is we observe that the Schema variety base change, since it's base change from spec E to spec EL, the ring class field, is actually equal to the Schema of same Schema variety with a slightly smaller level structure. So KG1 is a subgroup of KG, and its index is a normal subgroup with abelian quotient. So more formally, if we are given a character from G, in the case I have been saying is U1, but this can be GM. If we're given a character and we take the elements of KG where the character is 1 mod L, you get a slightly smaller level structure, and this Schema variety is related to the original one just by a base change. I should probably say this is true for almost all L. for small L's, you might run into issues as well. So on the one hand, what this says is to get classes over E adjoint L, not E adjoint L, that's a ring class field EL. All you need is to get classes for the Shimao variety with a slightly smaller level structure than the one you started with. And the top proposition says to get cohomology classes in Shimao variety with any level structure, you just need to find a function with the correct, which is fixed under that level. Right? So altogether, the Euler system relation becomes something purely purely a question of finding correct test vectors. So we need smooth compactly supported function of X. One of them shouldn't be there. They're the same. So we want KL1 invariant functions of X with ZP coefficient, or not with ZP coefficient, with ZP values, taking values in ZP, not QP. So this is function of X, which is invariant under KL1, taking values in ZP. And the condition for Euler system is that its trace from KL1 to KL is a specific Hecke operator applied to the indicator function. So I'm implicitly assuming L is unramified. In this case, KL is a maximal compact subgroup, and KL1 is a subgroup of KL, which is normal and has abelian quotient. In a specific case, like say G is U, let's say G is UN, the KL1, let's not even, let's just say G is GLN. That's the easiest. So KL would be the maximal compact subgroup. Let's just take GLN of ZL. There's something like KL1 would be integral matrices K whose determinant is 1 mod L. So this is a normal subgroup of index L minus 1. Okay. So we need to find a function which is invariant under KL1, whose trace, once you take trace down to KL, is the basic function, the indicator function of the maximal, the iramified part of X, with a specific Hecke operator applied to it. Okay. And our strategy is to first characterize the image of this trace map. And then that's basically about the geometry of X. So characterizing the image of the trace map and then use harmonic analysis to tell me that this lands in the image of the trace map. So we are never actually working with this space directly. Okay, so that's the goal. Any questions so far? Right. In the examples I have given you, Hegner points, of course, was the work of Polywagen, modulo this issue with the norm relation being slightly different. But essentially, this is the work of Polywagen. For the Birch-K case, the finding the correct test vector was done by Andrew Graham and Syed Wakar Ali Shah. And in the Gagros-Persad case, this was my work with Chris Skinner. But in all those cases, the test vector was chosen concretely, and a long unramified calculation was needed to prove this norm relation. The nice aspect about our method is I can prove all three cases uniformly. And I do not need to do any computation to prove any of the three cases. So we give a purely conceptual reason why such a test vector should exist. We never write down a formula for the test vector, which is really long in higher rank. Okay. So if there are no further questions, I'm going to start talking about the image of the trace. So from now on, until the end of the talk, I'm going to work purely locally. So F is a local field, L is the size of the residue field. Just a slight change of notation. And remember this variety X was G mod H. So it has a right G action. And before that, we were interested in unramified functions, which is functions on X, F, let's say ZP valued, which are invariant under G of O. O is a ring of integers. But because G of O is open, this is just the same as saying functions on X of F mod G of O, ZP. So this is a discrete collection of points. And it has actually a very combinatorial description. This was first proven in the function field case by Gates-Green-Nadler, and Sakharidis took their proof and worked out how to modify it appropriately in this mixed characteristic case. So roughly what it says is the X of F mod G of O is labeled by a cone. And more precisely, X of F has a disjoint union representation as cosets of G of O, where the representatives are explicit elements that comes from the geometry of spherical varieties. So I told you we are going to do two cases. So in the first free Birch-K case, this cone happens to just be non-increasing integers, positive integers. So A1 to AN are integers, and we need them to A1 to be at least A2, and so on, and all of them have to be positive, non-negative. So this is the cone in the free Birch-K case. Notice that this has only n variables. This is rank n. Whereas we recall in the free Birch-K case, G is essentially GL2n. So that's rank 2n. The fact that this lambda only has rank n is a reflection of something I'm going to talk about later, which is the Frick-Birch-K period only distinguishes symplectic self-dual representations. It doesn't distinguish everything. But in any case, this is very easily worked out from the geometry. In the GGP case, lambda just corresponds to non-decreasing integers of less n, non-decreasing integers of less n plus 1. So you can recognize this as exactly the positive rate chamber of the group G. So free Birch-K, you don't see all of the chamber, you see a quotient of the chamber. GGP, you see all of the chamber. Okay, so unramified functions, meaning functions which are geo-invariant, just corresponds to functions on those combinatorial data. And smooth doesn't matter anymore because I already had the smooth condition. So compactly supported still means compactly supported. So we are interested in finding a criteria on those functions which guarantees that it's actually the trace of something with a slightly smaller level. And that's one of our results that we prove using compactification. We basically also took the Gates-Green-Nadler proof of this Cartesian decomposition, but we modify it slightly to take into account the presence of certain line model. But it's basically the same idea. So if you know that proof, this would not come as a surprise. So the image of x of f k1. So remember, if k were something like gln of zp, then k1 would be the subset where determinant is 1 mod, not p, L. L. Determinant is 1 mod L. So under the trace map, the image, so this lies in the ironified functions. So when we can easily prove, I suspect this is an if and only if, but we don't need that part. All we need is it at least contains all functions satisfying this divisibility condition. Where at one of those representatives x lambda check, it has to be divisible by L minus 1, assuming a certain combinatorial condition that it lies on a wall of type T. So here are the two examples. In the GGP case, remember the indexes set are A1 to AN and B1 to BN plus 1. So there are obvious notions of walls, which is with one of those inequalities is actually an equality. That's a wall. As it turns out, all walls are type T. This is what's known as a strongly tempered case. So our general theorem tells us that if the value of the function is divisible by L minus 1 whenever two of those entries are equal, then it's in the trace. Actually, an explicit computation tells you this is an if and only if. The image is exactly the set of all functions which, when all of those numbers are distinct, there is no divisibility condition. And when 2 of them are equal, there is a divisibility by L minus 1. Notice that L is not the same as P. In practice, you are going to choose a prime L which is such that L minus 1 is very divisible by P. So this is a very non-trivial. This is a non-trivial statement. Okay, so that's the GGP case. But you do not see what I mean by wall of type T because, as it turns out, all walls are of type T. Friedberg K case is more interesting. Remember, in the Friedberg K case, we have A1 to AN, except the final one has to be at least 0. So there are obviously n plus 1 walls. No, n walls, exactly. The cases where one of those inequalities is equality. But in this case, there's only one wall that's important. This is the only one of type T. All the other ones are what's known as type G. It doesn't matter. So as a consequence, we only need divisibility if AN is equal to 0. It doesn't matter if 2 of the other roots are equal, unless AN also happen to equal to 0. So there is a distinction between walls of type T and walls of, let's just say, type G. This distinction is reflected in how we analyze the boundary structure of a spherical variety. Like all those root data are kind of related to the compactification. So, okay. Again, in GGP case, we need divisibility as long as any 2 roots are equal, not 2 roots. Any 2 numbers are equal. In the Friedberg K case, we only need worry about the case when AN is equal to 0. So that's the divisibility condition. Again, the proposition is necessary condition to light in the trace, but in the two examples we computed explicitly, it also happens to be sufficient. We only need the necessary condition. Okay, so once we have the necessary condition, now we want to go to the other side, which is, does this basic function apply, does this hacking operator apply to the basic function satisfy the conditions we found by geometry? So here, the hacking operator, remember I said the hacking operator should be some notion, should give rise to the local Euler factors. Hence the name Euler system. So it's not, so we are not describing the hacking operator concretely as a bunch of double coset operations. Instead, we are actually describing the hacking operator by a Satake transform. As let's say we have a representation, we know its Satake parameters, then I know exactly how L acts on the representation. It's some kind of product of 1 minus Satake parameter type. So since it's not given by an explicit double coset operations, it's hard to do this computation in general. But another idea in your paper is we use the relative Satake transform to calculate the action of this hacking operator. Remember, all of this is taking place in CC infinity smooth compactly supported functions on x of f. Let's say ZP, but ZP doesn't really matter that much. And it's G of O invariant. So everything is taking place in this space of functions, which can be described concretely. This is, in the cases presented, this is a theorem of Yannis-Sakalarides from 2013. So there is an isomorphism of the group we are interested in with a certain Y invariant vector acting on the space of regular functions on a torus. The left-hand side has the usual hacking action. Because this is unramified vectors and X has a G action, the hacking algebra naturally acts on it. And the bottom arrow is the usual Satake isomorphism. The top arrow is, I would call relative Satake isomorphism. And the point is, both sides are modules with respect to each real on either side of the usual Satake isomorphism, and this entire relative isomorphism is equivariant. And here, AX is naturally a quotient. AX is a quotient of A. Okay, let's give an example. And WX is a reflection group, is a wild group acting on AX. So in the GGP case, this is easy. AX is equal to A, WX is equal to W. So we are saying both sides, we are saying in particular this function space is a free hacking module of rank 1. Because the right-hand side is visibly, it's the same, it's reacting on its space. In the free Jacobi case, again, this is interesting. This goes back to my earlier point that this description only has rank n, whereas the group has rank 2n. So in the free Jacobi case, A is of course still just essentially C cross to the 2n. But AX has this symmetry. You have the first n entries which are completely free, but the others are determined by reflection. And WX is a root of type C, is the wild group for the root system of type C. Again, this is because in the Fourier Jacobi case, you are only seeing the symplectic self-dual representations. No. Symplectic representations. So all of those spherical root data has this additional requirement. So in the Fourier-Jacobi case, this function space is no longer free as a hacking module, but it's a very concrete module. Okay, from now until the end of the talk, I think I'm going to focus on the GGP case. And I'm going to mention where the free Birch-Jacobi case differs. Okay, so focusing on the GGP case, I can tell you in the paper where Yanis proved this isomorphism, he actually gave an explicit inversion formula for it. Okay, this is a scary slide, but most of the details doesn't matter. Like I said, I'm going to avoid any computation. But I put all the scary details there because this is correct as a statement. I'm just going to draw attention to the important pieces. Okay, so remember we had a hacking operation. Okay, so if I have a function phi here, I'm going to denote this image by phi hat. So the point of the next slide is if I'm given a function phi hat, I want to recover the function phi, and remember the function phi is just determined by its values on those co-roots, on those x lambda check, where lambda check, let's say, some cone. Okay. So this is the Fourier transform. This is a kernel function. More abstractly, this is the Planchier measure associated with the variety X. Some definition. Eventually, we get the value. The way we do this is the inversion formula was written as kind of an integral over a torus. But of course, integrating over a torus just corresponds to expanding the thing into a formal power series and taking the residue term, the coefficient -1. And all of this is just to do all of that in a more combinatorial way. So we get some kind of formal power series, we expand it, and as it turns out, the value of phi is just given by this kernel function evaluated. It's just given by certain coefficients in this kernel function, modulo powers of L. Like I said, the detail doesn't matter. The point is there is a formula, but we're not going to do computation with this formula. All we are going to look at it is the general shape of each individual pieces. Let's see if I should do the distinctions here or there. Okay, let's keep it here. Let's talk a bit more about the shape. In the numerator, you see a bunch of adjoint L functions terms. Those looks like adjoint. Well, not L function, L factors. So they are product of things like 1 minus alpha check, where alpha runs over all positive roots, not just simple roots, all positive roots. That would be familiar from the Gauss-Prasad conjecture, where adjoint L factors show up. The denominator looks like L of 1/2, something like Z cross W. Right? You get this exponent 1/2, and you get the product of two things taken over all I and J. But there is a crucial difference. We are not getting the full L functions. This exponent, if this exponent were always 1, this would be literally true. But it's not always 1, it's occasionally -1. So this is some kind. So in particular, the denominator is not Weil invariant. But so this is related, but not exactly the same. The L function, this is wild invariant. But this is like taking a positive chamber. This general shape carries over to all the other settings. In fact, that's what Yannis Sakarides spent a lot of effort in his paper trying to get everything into this shape. Okay, so we see adjoint L functions, we see some weird, some kind of local L factors with some weird sign change. And this is a feature. Okay, but forgetting all of that, it's obvious that everything inside, once you expand something like this into a power series, you are going to get integer coefficient, first of all, up to factors up to L to the power of 1/2. And if you work a bit carefully about where the fractional exponents show up, you can pretty easily show that you're always going to get values in Z adjoint L to the power of ±1. And in fact, it's going to be a polynomial in L to the ±1. So this is pretty immediate just from the general shape of the formula. I don't need anything specific about the kernel function. So integrality is fine because L is not equal to P. So now we need to worry about divisibility by L minus 1. To do that, we do a specialization argument. This was a polynomial function of L. We specialize L at L equals to 1. And this should say wall of type T in general. Okay, so we are reduced to this statement. We want to prove certain coefficients in a power series is equal to 0. And we do this by an anti-symmetry argument. So first of all, this is the local L factor. Remember, I should have the slides. Yeah, again, the slide is scary. Don't worry about the details. So this is a local L factor. This is actually the local L factor. And this denominator just looks like the L factor, but there are some sign issues. So when you take the product of the local L factor, the denominator cancels out if the sign is +1. Well, if this epsilon is +1, and it doesn't cancel out if the epsilon is -1. So the adjoint L factor stays the same, but we are left with this term. Ignore the adjoint L factor point. It doesn't really play a role. We are left in the product over when epsilon ij is equal to -1. So that's this. That happens to be this by the definition of epsilon ij. And you get 1 minus some product to the 1 minus A inverse over 1 minus A, which is just equal to minus A inverse. And we can do this because we specialize at L equals to 1. If we didn't, this would carry a L to the power of -1/2. No, right. This will This will carry a power of L to the -1/2. This would also have L to the -1/2, but the numerators will have a power of L to the -1 inside. So once you specialize at L equals to 1, all of those what I would call weight terms disappear. So we are only looking at some roots. We are not looking at we are only looking at things in the root space. We are not interested in the weight aspect. Okay. In any case, we have this fraction which becomes a polynomial. And when you multiply all of this together, this is a polynomial, this is a polynomial, this is a polynomial. So we get some polynomial in z to the ±1, w to the ±1. Because we have this cancellation with L factors. Now, remember for GGP, we want to show that as soon as any of the two exponents are equal, the result has to be 0. So we do by anti-symmetry. Let's say we switch two variables around. If I switch Zi and Zi plus 1, first term was the adjoint L function term. When you do a simple reflection, you get the root corresponding to that simple reflection out from this product of positive roots. Up with a minus sign. So the first term gets multiplied by negative Zi over Zi plus 1. This is just standard Lie theory stuff. But the second term is multiplied by plus Zi over Zi plus 1. That's just visibly from the shape of the second term. So if I do this switch, the function becomes its negative. But if AI is equal to AI plus 1, then I'm saying a number is equal to its negative, so the number is automatically 0. And similarly for the other operations. So this anti-symmetry argument automatically proves divisibility by L minus 1. What about the free Birch-K case? I said there is some modification. Free Birch-K case is not strongly tempered. So what that means is, in particular, in addition to the L factors that you expect to see, you also get a bunch of other L factors coming from like what's left over from the root system. So in the free Birch-K case, I'm not going to go into details, I'm just making a quick remark. There is some extra terms. Those extra terms, by the shape of the result, cancels out with certain terms here. The numerator is a root system for G, but we are interested not in the root system for G for the trace relation, for the trace divisibility. We are interested in a certain root system for the spherical variety. And those extra terms in free Birch-K in the free inversion formula for the free Birch-K case exactly matches with the extra terms in the numerator. So in the free Birch-K case, if the two numbers are if two of them roots of type G, if A1 is equal to A2, for example, we don't see any additional divisibility because, as it turns out, this sign is -1, this other sign is -1, so we do not get anti-symmetry, we get symmetry. When you have a root of type T, that's when you get this extra term. This extra term only comes, we only have this term when the root is of type T. So from a harmonic analysis point of view, roots of type T are also special. And they are special in the exact same way that the geometry dictates us. Okay, so all of this should be part of some general picture. I set up this function, smooth compactly supported function of X, mapping into certain continuous cohomology classes. But really, you can replace continuous cohomology by motivic cohomology. And then we have more examples. We already have those. For example, Ziegel units. And then you can push forward Ziegel units, for example, for this Euler system for GSP4 cross GL2. So one example of this is Ziegel unit, which is something that exists on the marginal curve GL2. But we can push forward the Ziegel unit to something like GL2 cross GL2. And on GL2, we have Ziegel units. The push forward collection of classes are those are the classes that were used by Lay-Loeffler service when they constructed Euler system for Rankin-Selberg motives, for GL2 cross GL2 specifically. There, they also had to do a bunch of annoying Heike operator computations, and OR method again applies to their case as well. So there should be some general formalism where we can construct motivic classes starting. We can construct motivic classes and index by test data, which are just functions of a certain variety X. The classes described by Chris and Marco last week should also falls into this general picture, but there's a harmonic analysis. It's actually more difficult and interesting. There's a spherical variety actually has singularities, so it's not strictly covered by BZSV. So once you have such a collection of classes, which might be constructed by this relative cohomology construction, it could come from arithmetic theta-live, like Daniel Disney has described before, or it could come easily just from diagonal cycles. Once you have this, our method could extend it to Euler system in a purely conceptual way. I glided over this issue of K1. The correct formulation is you should expect an S variable in the period integral representation. And that seems to be related to the existence of certain GM bundle over X, which I give the name combinatorially trivial. That's related to how much you can twist by a billion characters. And then remember this cancellation I described earlier in this GGP case I mentioned in the free project K case. Well, this cancellation is manifest in the description of the pressure measures that comes from this relative length program, BZSV, BenSV, cycloradius, Bengaluru. In their local arithmetic conjecture, they gave a conceptual description of the kernel. And this conceptual description of the kernel is exactly what we need to get the cancellations. Also, the conceptual description of kernel agrees with Yannis' work in all the cases where Yannis' work is known. Okay, so the upshot of this is there should be a strong connection between philosophy coming from the relative lengthless program and how we can construct Euler system and test functions. Okay, that's it.
Any questions or comments? Actually, I have one. So I kind of got a little lost on the Friedberg-Jacquet situation. You don't have to scroll back. It's a general question. So if you had do you get something on the derivative of the central L value for?
No, we don't do anything about derivatives. All the statements are of the form if the cycle is non-zero in Galois cohomology, then the Selmer group has rank 1. But we don't know how to directly relate the classic Galois cohomology to the derivative.
Oh, I see. Well, that's a program for you, I suppose.
That's not a program for me. I do not claim anything about that.
Any other questions or comments? Actually, I have one more. What is that exterminate? What's getting exterminated behind you?
Oh, me. I'm being chased by Daleks. This was from COVID times.
Okay. Okay. All right. If there are no further questions or comments, let's thank Shilin again.